here we're going to discuss a little about the algebraic properties of matrices. Now, matrices have many applications in math and other branches of science. One application, week 3, when we discussed maximizing profit with equations like 20x plus 15y equals 300 and something else. Those equations those systems of equations, we had 2 equations, those could be modeled, not modeled, that's not the right word, those could be translated into matrices, and then they could be solved using some properties of matrices. Now, we won't get to one of the computations that would be required in order to do that computations. We'll just stick to addition and multiplication here. So matrix addition and multiplication. What's a matrix? Well, definition, an n by m matrix. So here we have lowercase n times m. An n by m matrix is a rectangular array of real numbers with n rows and m columns. Well, let's look at 2 examples. Let's take this. When we put matrices in these square brackets like this, sometimes you see them with big parentheses. I like the square brackets. Right there. There's a matrix. How many rows? What is that A for? Well, it's for a sentence. Well, a fragment. How many rows? 1 row, 2 rows. Rows are the things going horizontally. 2 rows, how many columns? 1, 2, 3. So right here, we have a 2 by 3 matrix. Let's make another. 4, 1, 8, negative 3, 0, 7, 3, 1, negative 3. Right there, that's a square matrix down here, because the rows and the columns are both the same number. Here, 3 rows and 3 columns, which makes a 3 by 3 matrix. So we're going to look at addition, subtraction, and multiplication. So let's start with addition. Now, real number addition, like 5 plus 7, that is defined for all real numbers. Matrix addition is not defined to exist between all matrices. Matrix addition is defined only for matrices of the same size and is done by component. So let's look at this example. Right here we have a 3 by 2 matrix. We have another 3 by 2 matrix. So addition can be done. And what does it equal? Well, you do it by component. What does that mean by component? Well, the first row, first column position in the first matrix is 4. The first row, first column position in the second matrix is 6. 4 plus 6 is 10, and we put that in the same position there. And you do that for all of these. Negative 2 plus 9 is 7. 6 plus 1 is 7. 3 plus negative 2 is 1. 1 plus 3 is 4. And 0 plus 8 is 8. So that matrix plus that other matrix gave us this matrix. So that's an example matrix addition. And matrix addition was defined there. Let's look at what it would look like when matrix addition is not defined. Well, the 2 I had written here that I erased, you can't add those 2 together because they're different sizes. Let's look at another example of that. Example, this matrix, let's do 2, 3, 7, negative 1, plus, let's do, so right here we have a square matrix, a 2 by 2 matrix, 2 rows, 2 columns. Let's do a 3, 1, 7, 9, negative 2, 1, negative 3, negative 5. So we have a 2 by 2 and a 4 by 2. This addition is not defined. They have to have the same number of rows and the same number of columns. Another way of viewing that is, that having the same shape, you can just view, this matrix going like on top of the other one and superimpose them. And if they match perfectly, addition is defined. So that's matrix addition. Matrix subtraction is the same thing, except, so I'm going to be lazy. The next example is going to be this one with a negative between them. And I'm not going to formally define matrix subtraction like we did there. I'll just say matrix subtraction is just like addition. So, just like addition meaning it's defined only if they have the same size, and it's done by components, but here you're going to subtract. 4 minus 6, negative 2. Negative 2 minus 9, negative 11. 6 minus 1 is 5. 3 minus negative 2 is 5. 1 minus 3, negative 2. 0 minus 8, negative 8. And similarly, these two you can't subtract for the same reason. So matrix addition, subtraction are, well, I would say they are what you would expect them to be if they are defined. And you just do it by component. Matrix multiplication is not. Matrix multiplication is much more complicated. So let's discuss that next. Matrix multiplication, more complicated. Now, matrix multiplication, just like addition and subtraction, isn't always defined. But it's not just not defined when matrices don't have the same size. Matrix multiplication could exist for matrices which don't have the same size. So this example over here, we have a 2 by 2 and a 2 by 3. This multiplication will exist even though they don't have the same size. What will it be? Well, let's get there. Matrix multiplication, more complicated. So here, I'm going to take an A by B matrix, multiply it by a C by D matrix. So A rows, B columns, C rows, D columns. That equals an A by D, sometimes that equals an A by D matrix. The first row, the last column. So you can sort of see it as crushing the B and C away. But it doesn't always equal an A by D matrix. It equals an A by D matrix only when B equals C. So if you want to know whether matrix multiplication is defined, well, you need to count rows and columns for both of them and see if the columns in the first equal the rows in the second. And I always like to do that by well, I don't always like to. If I ever have to write that out, I like to do that by writing out the matrices in row by column. It's always row by column. That's standard. So it equals an A by D matrix only when B equals C. And we'll see in that example, with actual numbers, how that works. But there's one other remark about matrix multiplication to make. Matrix, well, comma, equals an A by D matrix only when B equals C, comma, and matrix multiplication is defined by, I'll put in quotes, row times column. So these are the two things we need to keep in mind, technically three things, for matrix multiplication. A by B times B by C, A by B times C by D equals A by D only when B equals C. A lot of letters. And is defined by row times column. What does all that mean? Well, let's look at this example. So here, usually you don't, and with matrices, you don't write out the dot in the middle for times, just put them right next to each other. So we have matrix 2, 3, 4, 1, and we have matrix 1, 3, 5, 4, 6, 2. What are these sizes? Well, first, well, I already told you this does exist, but why does it exist? Well, let's figure out this part. And if we figure out this part, it will also tell us, not only will it tell us whether it exists, it also tells us the size of our answer. So what do we have? 2 rows, 2 columns. What do we have here? 2 rows, 3 columns. These 2 middle numbers equal. B equals C. So matrix multiplication here is defined. Maybe I'll point that out. Equal, so multiplication is defined. I probably should have written the word equal, or whatever. What else does that tell us? Since they're equal, it tells us our answer is going to be A by D. Our answer is going to be this number of rows and this number of columns. So this answer is going to be a 2 by 3 matrix. Great. Let's draw out a 2 by 3 matrix. Well, let's draw out a shell of a 2 by 3 matrix. So we know multiplication is defined here. We know the shape of the final answer. How do we find the entries? Well, this is how we find the entries. Row times column. What does that mean? Well, there are a few ways you could see it. Take a row. Take a column. Multiply them. How do you multiply them? Well, you multiply them with addition. I like to see this by literally viewing this as going like on top of that other one. And if they match up, it'll be defined. But here, 2, 3, 1, 4, how do we do it? First entry times first entry is 2. Second entry times second entry is 12. 2 and 12. 2 plus 12 gives us 14. And where did that come from? 2 times 1 plus 3 times 4 from what is circled. These 2 multiplied plus these 2 multiplied. And then you keep going across these columns. You still stay with this row. And you just keep going across. So the next entry up here, well, notice also where this winds up is kind of where they intersect. You know, the first position, first column, they wind up in the first and first. Or you could just follow this algorithm that I'm about to describe. Stick with the first row, go to the second column. 2 and 3, 3 and 6. 2 times 3 is 6. 3 times 6 is 18. 6 plus 18, 24. Next one. Still with this row. You're going to take each row and like scan it through the columns. 2 by 3, or 2 and 3. 5 and 2. 2 times 5 is 10. 3 times 2 is 12. 3 times 2 is 12. Where am I going? 3 times 2 is 6. I don't even know where I would have seen 12 from. 2 times 5 is 10. 3 times 2 is 6. 10 plus 6, 16. Well, we're done with all those rows. We're done with the first row. There's nothing else we can do with the first row. So now, we'll do the second row. I kind of want to leave those circled. Maybe I should have made 14 blue. Yeah, I have the blue marker. I guess I can do that. just for illustrative purposes. That would make more sense here. 14, and that is 2 times 1 plus 3 times 4, from what is ovaled. Next. 4 and 1, and we still take that row and go through each column. 4 and 1, still line it up first position, second position, second position. So 4 and 1 on top of this, 4 and 1. 4 times 1 is 4, 1 times 4 is 4, 4 plus 4 is 8. And you do that with the others. 4 and 1 on 3 and 6, 4 times 3 is 12, 1 times 6 is 6, 12 plus 6 is 18. And the last one, 4, 1 on 5, 2, 4 times 5 is 20, 1 times 2 is 2, 20 plus 2 is 22. So all of that was done row by column, using inside that multiplication and addition. So right here, this matrix multiplication was defined. Let's do 2 more examples, one where it isn't defined and one where it is. Let's throw some negative numbers on. Well, this next one's not going to be defined, so it doesn't matter if we put negatives. Example. 2, 7, 3, 1, 6, 2 times, I'm not going to write the times dot, but I am going to move these over a little. 2, 1, 7, 3, 6, 2. How about let's do this? 6, 7, 2, 1, 4, 3. Yeah, I didn't say the right numbers. So first, is this defined? Well, this argument is very useful for figuring out the size of your answer. I find it not so useful for figuring out if the multiplication is defined, because it's always defined row times column. Does row times column work here? Well, try it. Row, column. 2 times 2, 1 times 2, 4. This 4 doesn't have something matching up with it. So right here, row times column isn't defined, because this isn't going to match up with that. So the multiplication is not defined. So that's directly using row by column. What if you did want to do the argument like that? Well, what would we have here? We have 3 rows and 2 columns times 3 rows and 2 columns. This, remember, the multiplication is defined if those are equal. So I'll say not equal. So the multiplication is not defined. So either argument, each argument, the just looking at row and column, that argument is the same as this argument mathematically. But I find the first argument, I find it less thinking than the second argument. And in general, I like steering toward less thinking for something like that. So let's look at another example. And this one, it will be defined. Let's see. Let's do a couple bigger matrices. Let's do one where you have to deal with 3 numbers. Let's do actually 2 more examples. Okay, this one. First, is this multiplication defined? Well, do a row times column. Row times column. Look at that, they match up. They both have three things, so it is defined. What's the size of the final answer? Well, for that, I'll figure out this way. We have a 3 by 3, and here we have a 3-row, 2-column. A 3 by 2. Remember, it's always rows, the horizontal things, by columns, the vertical things. These are equal, so it's defined, and the final answer will be a 3 by 2 matrix. What's a 3 by 2 matrix look like? Well, it has 3 rows and 2 columns. It looks just like the second one. As was the case in the first multiplication example we did, it wound up just looking like the second one. Is that always true? Well, no. So let's look at the entries. Well, we have these 3 and these 3. 2 times 3 is 6. 1 times 7 is 1. 1 times 7 is 7. 7 times 0 is 0. 2 times 3 is 6, plus 7, plus 0. 6 plus 7 plus 0. 6 plus 7, 13. Next, we still have another column to do, so we stick with this row. This row times the next column. 2 times 1 is 2. 4 times 1 is 4. 7 times 6 is 42. 2 plus 4 plus 42. 2 plus 4 plus 42. 48. Yes. Well, nothing else we can do with that first row. So next we'll go to the next row. This row times that column. Negative 2 times 3 is negative 6. 3 times 7, 21. 0 times 0, 0. Negative 6, positive 21, 0. 21 minus 6 is 15. Next, we still have another column to take care of. Negative 2 and 1 make negative 2. 3 and 4 make 12. 0 and 6 make 0. So we have negative 2, 12, 0. 12 minus 2, 10. And finally, we have this last row. So what do we have here? 1 and 3 make 3. Negative 4 and 7 make 28. 5 and 0 make 0. So we have 3 minus 28 plus 0. 3 minus 28, negative 25. And finally, this last row times this last column goes in this last entry. 1 times 1 is 1. Negative 4 times 4 is negative 16. 5 times 6 is 30. So we have 30 minus 16 plus 1. 31 minus 16 is 15. And let's look at one more example. Last example. Is this multiplication defined? Well, does a row match with a column? Row, you put that row on top of that column, it all matches up. So it is defined. What's the size of our answer? Well, based on example 1 of multiplication and this example multiplication, you'd expect it to be the size of the second matrix, 4 by 2. But, nope. No. Sorry, I get rows and columns mixed up all the time. I always have to remind myself rows go horizontally. It's very, I'm assuming it's related to how I don't know left from right off the top of my head. rows, the horizontal, there are 2 rows and 4 columns. There are 4 rows and 2 columns. The middle numbers match, so our final answer is a 2 by 2. Which is nice, because there are only going to be 4 multiplications to deal with. So it's a 2 by 2. Now each thing has 4 things to add, but, you know, whatever. So what do we get? First entry. 3 times 6, 18. Negative 2 and 2, negative 4. 7, negative 3, 21, negative. 6 and 4, 24. That's a lot of numbers. 18 minus 4 makes 14. Minus 21, negative 7, positive 24, 17. First entry times first, 3 times 6, 18. Negative 2 times 2, 4, 3, negative 3. Or sorry, 7, negative 3, negative 21. 6 and 4, 24. Well, we're not done with that first row. We have to go to the next column. 3 times 3, 9. Negative 2 times 7, negative 14. 7 times 0, 0. 6 times 1, 6. So what do we have? 9 minus 14, negative 5, plus 0, plus 6 gives us 1. Well, that's all we can do with that first row. Next row. Negative 1, 0, 5, 8. Negative 1 and 6 make negative 6. 0 and 2 make 0. 5 and negative 3 make negative 21. Oh, that's where I got negative 21. Okay. I got negative 21 because negative 6 minus 15 is 21. Negative 21. 5 and negative 3, negative 15. 8 and 4, 32. So we have negative 6 plus 0 minus 15, negative 21 plus 32, 11. And last, negative 1 times 3, negative 3, 0 times 7, 0, 0 times 5, 0, 8 times 1 is 8. So we have negative 3 plus 0 plus 0 plus 8, which makes 5. So I would like you to practice the matrix multiplication questions and addition. Multiplication's far more interesting than addition, I think, and subtraction. But one interesting property, numbers, real numbers, regular numbers. 2 plus 3 equals 3 plus 2. 2 times 3 equals 3 times 2. Addition and subtraction of real numbers is commutative. You can do it in either direction. That's not the case with matrices. And you can check. This one, well, you can check with either of these examples. This matrix times this matrix gave this. What if you flip them around? Well, you flip them around. So we did the multiplication in this order. What if we do it the other order? Well, the other order, you're going to get a 4 by 4 matrix. A 4 by 4 matrix is not going to, it's not the same size as a 2 by 2 matrix, so it can't be equal. So just from this, matrix multiplication is not commutative. It's not even necessarily the same size. It's not even necessarily defined. If you flip those two around, they happen to both be defined. But here, if instead of doing this one times this one, you did this one times this one, you would have a 3 by 2 times a 3 by 3. These aren't equal, so that's not even defined. So matrices are, they're really the first type of example where something isn't commutative with addition, or something isn't, well, you're told through most of your math lives, addition is commutative with numbers, multiplication is commutative with numbers. With matrices, addition is commutative. But the first real example of multiplication not being commutative is with matrices. And you can see it can be commutative. There are properties they must satisfy for it to be commutative. But here, you do, instead of this one on the left, this one on the right, you put this one on the left and this one on the right, you get a matrix with a different size, so they're not equal. If you flip these two around, you don't even get that the multiplication is necessarily defined. So that's just one of many interesting properties matrices have. And in fact, linear algebra, the course linear algebra, is all dealing with matrices and using them. But I would like you to practice the multiplication especially. Always remember, row times column. The horizontal things go first, the vertical things go second.